Hello and welcome. Today we are going to be talking about something that's just so very important. It's compound interest. Now, we've already talked about simple interest and how interest is really just extra money that you pay to use someone else's money. Well, simple interest is calculated just one time. It's one formula. It's a very simple formula. It's that I equals PRT formula. But today we're going to be talking about what happens when we calculate a little bit more. You see, compound interest is another way to pay or charge interest on a loan, and then it allows you to earn that interest, right? If you're on the receiving end of that. With compound interest, the interest is calculated several times or many times over the course of the loan. The interest accrued is added to the principal before the interest is calculated again. The result is that the interest being accrued, or in other words, you're earning interest on the interest. So you're getting paid some interest, and then they're going to recalculate it, and then they're going to give you more interest, and then they're going to give you more interest, and then they're going to give you more interest. And so this can get a little repetitive. Let's go ahead and take a look at the difference between a simple interest and a compound interest problem. So here's our formula. $1,000 is invested at 2% per year. So $1,000 is invested. That's going to be our nope, not our I. That's our principal. So our principal is $1,000. 2%, that means our R is going to be 0.02, and it says for a year. So our T is 1. When we use our formula, we end up getting $20. So over the course of 1 year, if you invest $1,000, at the end of the year, the bank would put would put $20 in your account, and you would have $1,020 in your account, but you will have earned $20 worth of interest. Let's look at compound interest now. $1,000 invested at 2% compounded twice a year. So it seems like it's the same thing. $1,000 invested at 2% for a whole year. But this time, because it's compounded, we have to treat it a little bit differently. What's going to happen is this 2% that we have is going to be split up over the course of 2 different time periods over this year. So instead of saying that R is equal to 0.02, we're actually going to take that and split that in half because it's compounded twice a year. So we are going to be using 0.01 for our rate, and we're just going to do that 2 times. So let's get this plugged into our formula where P is our 1,000, and then we're going to do this for one time period, so to speak. So I equals PRT. So at the end of the first period, or at the end of 6 months or half a year, we have about $10 worth of interest. And that should be kind of what you would expect, because we know that under simple interest, we get $20 for the course of the whole year. So it would make sense that over the course of half a year, that we would get half that. But this is where it gets a little bit interesting, because after 6 months, the bank puts that into your account, and now your new principal is not 1,000, but your new principal is actually going to be the original 1,000 that you had in there, plus that $10 that they gave you for interest. That's $1,010. So let's use this $1,010 as our new P. Notice this time we get more than $10. In fact, our total interest that we've earned over the course of this year is equal to these 2 amounts added together. The $10 they gave us at half a year, and the $10.10 that they gave us at the end of the year. That's a total of $20.10 worth of interest. So because it got compounded, we ended up with more money than if it was simple interest. And it's kind of strange to think about, but the reason for that is because they gave us some of that money earlier. If they updated our account, if they gave us this $10 worth of interest like July 1st, notice that that's why we have a larger principal. And so when the principal gets larger, then your interest is also going to get larger. So that's how compounding works, is they pay you a little bit of interest after a little while, your account gets bigger, and because your account gets bigger, when they pay you interest the next time, you have even more interest. Next, let's explore what happens if instead of doing this twice a year, what if we did this 4 times a year? Now, I don't actually you don't need to do this. Okay, this is twice a year. This is just for demonstrational purposes. So I'm going to say quarterly, which is 4 times per year. So hopefully, we think of quarters as in 4 quarters in a dollar or whatever. So quarterly means 4 times per year. Let's take this $1,000 and do that. I'm going to start out with my 0.02 interest rate over the course of the whole year. And we're going to split that in 4 because we're going to do this 4 different payments throughout the year. This comes out to be 0.05, or in other words, 0.5% interest each quarter. Let's go ahead and use our formula. Again, that's probably what you would expect is if we're doing it for 1/4, we would get 1/4 of the interest, so $5. So after 1/4 of the year, or 3 months, your new balance in your account is going to be $1,005. That's our new principal, and that's what we're going to use for the next compounding, so to speak. Here we get $5.03. It was a little more than $5, or a little more than $5.02, and then it just rounded up to $5.03. So now the bank is going to put that into your account, and what will happen is your new principal in the account is going to be $1,010.03 because they add that interest in. Let's go ahead and do that again. That's how we get $5.05 worth of interest. Notice that our interest is increasing each time period. You can see the amount of interest we got in the first time period was $5, then $5.03, now $5.05. That's because each time our new principal was increasing from 1,000 to 1,005 to 1,010. Because that principal was going up each time, the amount of interest that we gained went up each time. Let's do our last compounding now. I went ahead and rounded to the nearest penny, and then if you go through and you add up all of our interest amounts, you can see we actually have $20.16. So when there was no compounding, or when we did this just 1 time per year, we got $20 of interest. When we did it, when we compounded it for twice per year, then we ended up with $20.10, I believe. When we did it 4 times per year, we got $20.16. So in general, what we can say is the more times you're compounding, the more money that you'll make. It doesn't feel like a whole lot. It's only a few cents in this case, but that's one of the beauties of the power of time. Over time, these couple of cents here and there and these little extra compoundings are going to add up to large amounts of money. We'll look at a few examples a little later. But that's just kind of how compounding works. This is a whole lot of work. If only there was a nice way of doing this so we didn't have to do 1, 2, 3, 4 steps. And this is, of course, only for 1 year. Well, that's where our compound interest formula comes in. The compound interest formula is this one right here, which is just A equals P times the quantity 1 plus R over N to the NT power. You'll notice there's a couple things that should look a little familiar. You can see right here we have R over N. That was the same thing I did here. Now this 1 plus just deals with us adding it together because we want to grow by that much. But let's look at each one of these parts. The A is the amount in the account. Sometimes you'll see some books refer to this as the future value because generally speaking, the principal is what you start with, or the initial amount, and then A is the final amount in the account. So sometimes you'll see FV for future value, which is would be the same as the account, and you'll see PV for the principal, which stands for present value. Just be aware that different books, I've seen this formula as FV instead of A and PV for P. I probably won't use that. I'll talk about it in terms of future and present value at times, and we might run into that some other formulas. Just be aware that that's what it is. R is our rate. It should always be expressed as a decimal. And then T is our time, which we're going to be using in years. N is the number of times the interest is compounded per year. These are things that you should memorize. They should kind of make sense, though, because annually just means one time per year. Semi-annually, that means every half year. So in other words, you'll do that 2 times per year, right? Quarterly, we've already talked about. Quarter means 4. So a lot of banks actually compound quarterly. A lot of banks will also compound monthly. So just be aware of that. 12 months in a year, 52 weeks in a year. And then daily, we're going to use 365. Occasionally, you actually might see some banks use 360. It's not necessarily wrong. We're just not going to do that, and we're not going to get into that. That's something just called the banker's rule. Let's look and see how this compounding formula is going to work. You know what? Before we do, though, I do want to let you know that yes, this n does show up 2 different times. I want to kind of remind you of that. So that same number, that number of times that it's compounded, that shows up both in the denominator here and it shows up in the exponent. Be aware of that. You also might want to be careful if you're using a calculator like a single line calculator. You may want to come up here and add in a little set of parentheses right here like this. So we'll look and see kind of like why you might need to do that. If you're using Desmos, we are going to also do that, and you'll see why we need to. Okay. The formula isn't written with that parenthesis in it very frequently, though. After passing of his grandparents, Kyle inherits an IRA. This is called an individual retirement account, with a balance of $38,000. Kyle decides to leave the money invested and make no additional contributions until he wants to buy a house. The account earns 7% interest compounded annually. Calculate how much the IRA will be worth after these different time periods. So the first thing that I want to notice is it says it has a balance of 38,000. That's going to be P. That's our initial or our principal amount. Kyle decides to leave the money invested. In other words, he doesn't necessarily need it. He could run out and buy a new car with that right now if he wanted to. But he said, you know what? I'm going to save it for a house. The account earns 7% interest. I'm going to use R is equal to 0.07. It's compounded annually. So we're going to say N is equal to 1. How much will it be worth after 10 years? So that's going to be our T. Our formula, it's written right up here. It's one that you should write down enough times until you have it memorized, but it's just A equals P. I want to stop here because this is not right. And this has to do with the parentheses. If you look at my calculator right now, it doesn't look exactly like what I've written down over here on the left side of the screen. Specifically, this part right here doesn't look to be the same. That's because Desmos actually wants us to use parentheses when we want to put several things up in an exponent. So I'm going to back this up and I'll open a parenthesis here and then do 1 times 10. I could have just done 10. I just like to be in the habit of using that 1 because it's not always going to be compounded annually. If this was monthly, that both of those ones would be a 12. If this was quarterly, both of those ones would be a 4. But you could see that what does happen is he ends up with $74,751.75. So if he didn't go out and buy a new car and he just let that set for 10 years, he would have $74,000 to use maybe as a down payment on a house. Let's look and see how that changes, not when we're doing 10 years, but maybe he doesn't need it for 20 years. He has $147,000. By investing $38,000 and just letting it set, he has $147,000. That seems kind of crazy. But if you think that's crazy, let's go to this last one here. Because for the last one, you can see that we're going to let it set for 50 years. He inherits this at age 18 and he says, that's really cool. I'm doing good. I'm just going to put this away and I don't need it. Well, in 50 years' time, when he's 68 years old, and he would have $1 million just by letting it set. Um, that's pretty amazing. And that's the power of compound interest. Now I know you're like, this is ridiculous. This isn't real money. This actually is possible. 7% interest, while it's not an amount of interest that you're going to find from a bank very frequently, you're not going to just walk into a bank and say, hey, do you have a savings account at 7% interest? But investing something in stocks or land or lots of other investments can pretty frequently yield 7% interest or more. So these are some real numbers. If you can take some money and invest it at 7% interest and let it set, you can see that you do end up with some pretty sizable growth over the course of time. Now, you also notice I actually wrote this out every time, and while that may have that may have seemed to be a little bit excessive, that's how I learn. I learn with repetition. That's why I wrote those out each time. I also wrote the formula out. I put the numbers in each time. And then also, even in Desmos, I went through at least 2 of the times and retyped it in until I'm very comfortable. You see, this problem actually could have been done very, very simply just by saying, I could have just went like, well, there's 10 years, there's 20 years, there's 50 years. I could have been done with this problem in about 20 seconds and just written on all those numbers. But I don't know that I would have learned as much or had quite as much practice with the calculator. So I would definitely encourage you to do that until you're very comfortable. That is one of the really nice things about Desmos is you can change stuff around anywhere in here pretty easily. One last thing, I do want to show you the difference of compounding. If this same account was compounded monthly instead of annually, you can see we actually end up with $1,245,000. So that's a sizable difference. It's over $100,000 difference if something's compounded monthly versus compounded annually in this case. Let's talk more about finding interest. The compound interest formula that we just looked at calculates the total amount in the account, not just the interest that is being accrued. That's not like the other formula that we did. Our simple interest formula was I equals PRT. Notice that when we put values in for the principal and the interest, we end up getting, principal, the rate, and the time, we get the interest. But that last formula we did gives you the final amount in the account, A. Well, the final amount in general, your final amount is just going to be the principal plus the interest. And so we got to be careful because some questions will say, how much interest did you gain? Since the value of the account is composed of only the amount invested, which is your principal, and the interest, the extra money that's earned, we can solve for the interest. All we've got to do is subtract the principal. And if we subtract the principal from both sides here, that's where we end up with A minus P equals I. Don't get too confused by this formula. Like all we're doing is we're saying that when you use this formula to solve an equation, you're getting the final amount in the account. And that total amount is all of your original money along with all of the interest. So if you want to find just the interest, you got to subtract off the original amount. That's all. Nathan invests $25,000 into a diversified investment account to help pay for a future home down payment. It's good he's thinking about that. The account earns 6.5% interest compounded monthly. How much will the account be worth, and how much interest will Nathan have earned in 3 years? Well, as I was reading this, I want to identify the fact that this actually has 2 questions involved. How much will the account be worth is one question, and the other question is how much interest will he have earned? Okay, so there's two different questions here, and I want to make sure that we do actually answer both of them. Let's go through and identify the important parts of this problem. So the first thing that I see is the $25,000 tells me that P is equal to $25,000. It also tells us the account earns 6.5% interest. Remember, we don't write 6.5%. We're going to change that to a decimal. So I'll write that as 0.065. Remember, to change a percent into a decimal, you just divide by 100. It does say that this is compounded monthly. That tells me that N is going to be 12. Anytime I see that, compounded monthly, N is 12. Next, it does say after 3 years' time. That tells me that T is equal to 3. We are going to use our formula, A equals P, 1 plus R over N to the NT power. Again, it's a good idea to write this out every time until you have it memorized and you know the situations you're using this in. Let's go ahead and substitute all the numbers into this equation. Next, we'll put this into our calculator. So you can see the final amount in our account is $30,366.79. Now, that does answer our first question that we had. How much will the account be worth? That's this answer here, $30,366. But the second question, the one that says how much interest will he have earned, remember, interest is the extra money. And so since we started out with $25,000, we actually need to subtract off that initial investment so that we can see how much of it is extra. And when we subtract that, we should get $5,366.79. This is the amount of interest. Let's go ahead and keep moving on here. Solving that compound interest formula that we've been working with, again, that compound interest formula is just this formula here. Solving that formula for the principal is going to yield what's called the present value formula. Let me just do that real quick. If we take that formula and copy it over, and now if I work on solving for P by dividing both sides by 1 plus R over N to the NT power, we get the present value formula. And you can see that's the same thing that we had down here. I just wanted to show you how it was derived. What this is useful for is if you have an idea of some amount of money that you want to have in the future, this formula will tell you how much you need to invest right now so that you can reach your goal. Let's look at a practical example. Blake wants to have $200,000 available to him in 20 years to use as a down payment on a rental property. How much should Blake invest now if he expects to have an 8% return compounded quarterly? So there's a couple things that are very important here. The first is that I notice it says he wants to have. Wants to have, that means that's a future value. Remember we talked about how future value is sometimes the A in our formula. Some people talk about that in terms of the future. Our A value is 200,000, the final amount. I see that we have 20 years time, so T is 20. It says that we're earning 8% interest. I'm not going to use 8%. I'm going to use 0.08. So I'll cross that out and write 0.08 there. And I also see that it says compounded quarterly. That tells me that N is equal to 4. Next, we'll go ahead and substitute all of these numbers into our formula. Now, when you look at my calculator, notice that my calculator doesn't look quite exactly the same as the equation that I have on my paper. And this is a really easy mistake for people to make. I didn't put parentheses on the 4 times 20. Now, you don't have to actually write them that way, but in order to do this on the calculator, we do have to put them in parentheses. If you're using like a TI-84 or some of the higher end Casio, CG50 or whatever, they might already write things up in the superscript for you, and you might not have to use parentheses. But we're going to be mostly using Desmos, so I'll go ahead and fix that by putting that in there. Notice now that we have a much different answer. This is the final amount. This is, I shouldn't say the final amount. This is the amount he needs to invest in order to end up with $200,000. If Blake puts away $41,021.95 in an account that earns about 8% interest compounded quarterly, then in 20 years, he'll have $200,000 available to him for this investment property. Jessica also has plans. She wants to return to school in 5 years, and she wants to have $18,000 saved up in that time. If she invests 6% interest compounded daily, how much should be invested today to reach the goal? So again, let's identify the important things. I see that it says how much should be invested today, right? That's the thing that we don't know. That's the I don't know, and that's the principle. That's the thing we don't know. In 5 years, she wants to have $18,000. That tells me that my final amount, or that future value, is $18,000. 5 years, that's our time. I see 6% interest, so R is going to be 0.06. And then I do see compounded daily. That means N is 365. When we go through and substitute everything into our formula, and then we plug this into our calculator, we do end up getting a little over $13,000. If she were to invest this much right now, then in 5 years from now, she would have approximately $18,000. So that's the difference between the present value formula and just the compound interest formula. To be honest, it's the exact same equation. You're just solving for a different variable in each one. In the present value, that's how much do I invest now to reach my goal? But in the compound interest formula problem, like this one, this is, hey, if I have some amount of money now, how much will I end up with in the future? Okay, so that's the difference between those two equations. The next thing we're going to look at is called effective rates. Sometimes this is called APY. And simple interest is often calculated once over a whole some time period. And it is thus simple to calculate, hence one of the reasons it's called simple interest. Compound interest is calculated many times or several times. Since interest accrues on the principal amount and the interest, it's a little bit more challenging to determine the resulting fee on a loan or how much interest is earned, just a little bit. Effective rates show the actual or the real rate of return on a loan when the effects of compounding over time are considered. It's going to allow you to compare several different rates and different compoundings with what the equivalency would be on a simple interest loan. So, for instance, let's consider investing a $1 investment at 5% per year. Well, with simple interest, that's relatively easy to do. I equals PRT. We're going to invest $1 at 5% for 1 year. Our amount of interest then is just 0.05, or in other words, about 5 cents. When we do this with compounded monthly, now what we're doing is we're still going to say, let's invest that $1 at 5%, but compounded monthly, and we'll see what happens. A little over $1.05. Now, we only get paid out to the nearest penny, which would be 1.05, and that looks the same, but notice there's actually a little bit more to it. If we end up subtracting off that $1 initial investment so that we can find the actual change that has happened over this time span, we get this. Notice that our interest is a little bit bigger when we're compounding it than it is when it was just the simple interest. See, effectively, the 5% compounded monthly returns an amount that is actually $0.051162. It returns a little bit more, like fractions of a penny. You get more. Therefore, we would say that the real, or the APY, or the effective rate, however you want to think of it, is actually 5.1162% interest. Even though it's a 5% for the year, because it's compounded, it amounts to a little bit more than 5%. The effective amount is a little more than 5% because it's compounded 12 times over the course of the year. This 5.1162 is called the APY, or the annual percent yield. Now, I already did this, but you can see it's really just the same formula that we've been using, 1 plus r over n to the nt power, but t is going to be 1, so we don't need to write it. And then we subtract off 1. Remember, the reason we subtract off 1 is because that's subtracting off the initial investment so that we can find the change in the account. Remember, our time is just 1, so it's really kind of like saying n times 1, but we don't really need to write that. This formula finds the difference between the account value after compounding for 1 year and the principal. Remember, we're starting with $1. R is the simple interest rate. Remember, always use it as a decimal. And n is the number of times per year the interest is compounded. Remember that the formula is calculating a rate, and so that decimal, we do need to convert it over into a percentage to interpret it. Interest rates, even APYs, annual percent yield, are always expressed as a percent. Let's calculate a couple APYs, or at least work with some of these formulas. A high yield savings account advertises 4.75% interest rate compounded monthly. Determine the effective annual yield and explain what this rate means for someone who leaves their money in the account for a full year. The first thing that's important is 4.75%. I'm going to rewrite that as 0.0475. Just divide it by 100. We can see it's compounded monthly. That means n equals 12. And it says determine the effective annual yield. That's APY. That's what we're looking for. So let's write out what our formula is. Now let's substitute our numbers in. Our APY is equal to 4.85%. So what this means is, even though the person is investing in an account that says 4.75%, if they were, then that's compounded monthly. If they were to invest in a simple interest account at 4.85%, they will effectively get the same thing. The person will earn 4.85% interest on their money over 1 year. Or you could say a 4.85% simple interest account will bear the same amount of interest as a 4.75% interest rate compounded monthly. A credit card advertises an interest rate of 19.9% on unpaid balances compounded daily. Determine the effective annual rate and explain why carrying a balance for a full year costs more than the advertised rate suggests. The credit card is advertising 19.9%. This is actually a reasonable rate on credit cards. I personally wouldn't want to pay this, but I don't carry a balance on any of my credit cards. That's a personal thing. Some credit cards go up over 30% interest. Some of them are as low as 9 or 10%. It just kind of depends on your credit, but that's neither here nor there. For this problem, we can see that 19.9% I'll write as 0.199. It does say compounded daily, so n is 365. and then determine the effective annual rate, or in other words, APY. So let's go ahead and write our formula and substitute our numbers in. The APY for this credit card would actually be about 22%. I like to take my percentages usually out to about 3 decimals on the percent. This doesn't say what to round it to, so just round to whatever's important. A lot of times banks or whenever you're dealing with money will go out to about 3 decimals on the percent. Even though the bank is advertising an interest rate that's under 20%, because it's compounded daily, after a year, it would really be more like 22%. So it kind of draws you in by advertising a lower rate. It's not really a lower rate, but they're advertising it and then just hoping that maybe you don't understand the idea of compounding. So if you had two credit cards and one of them said simple interest rate of 22% and one of them said, hey, we have a 19.9% compounded daily. A lot of people might be swayed to go to the lower interest rate because they see lower rates, that's better. But really, they would actually be the same. A financial firm advertises a 5% annual rate of return on short-term investments. In the fine print, the return is calculating using a rate of 4.88% interest compounded monthly. Determine the effective annual yield and determine whether the firm's advertising is misleading, even if the stated numbers are technically correct. When we go through and identify these, it says in the fine print the rate of return is using a rate of 4.88%. We'll use R as 0.0488. The reason I skipped over the 5% is that's what they're advertising, but in the fine print that says they're using 4.88%. And our goal is to determine whether or not this 4.88% actually gets you to the 5%. It does say compounded monthly, so N is 12. Let's go ahead and substitute these into our formula. You can see that if we take 4.88% interest and we compound it monthly, that will result in an equivalent or an effective yield of about 5%. And in fact, if we round to the nearest percent, or even if we round to the nearest tenth of a percent, that would be 5%. So technically, it is kind of correct. It can be a little misleading. They're advertising 5%, but they're really paying you 4.88% compounded monthly. I mean, is it wrong? No, it's just kind of how the system works anyway. So read the fine print, make sure you're understanding that they're not paying you 5% compounded monthly. They're really paying you 4.88% compounded monthly, which will grow to about 5%. The last thing that we're going to do here is to look at this idea of the more often something's compounded, the more interest you'll earn, or in other words, the APY. Given a rate of 7%, calculate the effective yield when the interest is compounded annually, monthly, and even daily and hourly. This is N equals 1. Monthly will be N equals 12. Daily will be N equals 365. And then hourly, N will be whatever 365 days times 24 hours in a day will be. We'll get to that in a minute. All I'm going to do is go through and substitute all these into our equations, and then we can compare and see the differences. So we can see that the more compounding that happens, the higher our interest goes. But it does kind of seem to be a limit, because notice that when we go from annually to monthly, that's a reasonably large jump, like 0.229 of a percent. That's pretty significant. But when we go from monthly to daily, it's only a little bit of a jump. And then when we go from daily to hourly, it's almost no jump at all. It does kind of seem like there's some limit to the amount of compounding that we can do. Like we could even compound every second, every tenth of a second, every nanosecond, whatever. Carry this out. forever. There is a limit, and you might explore that in biology. It actually has something to do with something called Euler's number and the number E, but that's not for this lesson. I would strongly encourage you to go look that up, though, because it does have to do with, we use that model a lot of times for biological growth, where there's not some finite amount of compounding. Anyways, I hope that the things we talked about in this lesson made sense. I hope that you're able to have a better understanding of how powerful compound interest is. And in future lessons, we'll look at how we can leverage that to really start to plan for our future, to plan for retirement, or even just large goals that we have in life. Thanks for your time. Have a great day. Good luck.